Hey, so I want to walk through the IEEE 754. This is going to be the calculation for the normal floating point calculation. Uh, just want to forewarn you, I am not an instructor. I'm a student like you. And I really struggled with this concept after reading the textbook. It really wasn't that clear for me. So I put this together to solidify what I had learned. And I'm hoping that as I walk through this, it might help a few of you as well. So let's get at it. The value as far as the formula goes. So the value for IEEE 754 is -1 raised to the sign bit multiplied by the mantissa multiplied by 2 to the e. So let's say that we are given, for our program assignment, let's say that we are given a 4, 4, and a hex value of AF. So this is going to be our fraction. This will be our exponent, and again, x. So the steps that I would take, you can do this however you want, but the first thing I would do is I would convert the hex into binary. So we'll say that step 1 is going to be convert hex. And you can use, if you have, or you're on Windows, I don't know about a Mac, but on Windows, you can open the calculator, go down to programming. And if you're going to convert hex to binary, you'll want to just click on hex. Go ahead and enter AF. And bam, there is your binary. So 1010, 1111. Of course, at this point, you probably do know how to do this, and that will just make it a little quicker. So we're going to have a binary here of 1010, 1111. All right. Next thing I do is I'll just partition this. So the first 4 bits are assigned to the fraction field. The next 4 bits are going to be assigned to the exponent field. And we are 0 padding the higher order bits. So in this case, we're going to have to add that 0 for the sign bit. And then in the next step, I would just clarify what that stands for. What I mean by that is I'm going to divide that up as fraction. So the fraction field, it's going to be 1, 1, 1, 1. And its decimal value is going to be 15. So this is binary and decimal. And the next one is our exponent field. And its decimal value is 10. And then finally, our sign bit. So we have a 0 sign bit. And if we take -1 to that 0, or the sign bit, we know that we're just going to get 1. The next step is I'm going to look at the exponent field and I'm going to ask myself, is it either all zeros or is it all ones? If it's all zeros, then this is going to be a denormalized calculation. If it's all ones, then we have 3 possible special cases. So real quick, I just want to bounce over to a PDF that I put together. This is what I was doing to clarify my own thoughts on the program, and then I decided to just clean it up a bit and make it available. So if you're not a video person, you can just step through this and check out the normal and denormal calculations that I did or formulas that I'm using, as well as the special cases down below, which are pretty self-explanatory. There's not a lot going on here. As far as calculating goes, it's just a matter of parsing your fields correctly, making sure you zero pad the higher order bits. So if you click on this camera right here or down below, it's going to get you a video. In this case, it'll be of the one I'm making now, and that's going to be on normalized calculations. I did this in white, blue, and gray, or white, blue, and gray, depending on what you like. So hopefully that help you out. All right, so we have converted our hex value to binary, broke it up into the 3 fields. We're going to be using these values, these decimal values, in our calculations below. So we are now on step 3. And what I would do in step 3 is find the bias. And what's nice about the bias is it's going to be the same for denormalized or normalized. So you're going to calculate it exactly the same. So to find the bias or calculate, we don't need to find it. All right, so we're going to have bias is equal to 2 raised to the k less 1 minus 1. Now, in this case, k is going to represent the the number of exponent bits, or the number of exponent bits, the exponent field bits. So number of exponent bits given. We were given 4. So we're going to have 2 raised to the 4 less 1, all of that less 1. And 2 to the 3, we're going to have 8. 8 less 1, we have 7. So we have the bias. So now we're on to step 4. And at this point, I would do the fraction value. So let's find that. And for normal, to calculate this, this is going to be equal to our floating 1 plus the decimal value of the fraction. So up above, we found that the binary representation was equal to 15 as a decimal, or base 10. So we would have 1 plus 15 over 2 raised to the number of bits given. So the number of bits given for the fraction field was 4. So now we're going to have 1 plus 15, 2 to the 4, 16. And this is going to be 16 times 1, 16 plus 15, 31 over 16. And that is, back to scientific. All right, so 31 divided by 16, 1.9375. Awesome. So we are finally at the final stage of this mess. We are going to finalize the floating point. So number 5, we're looking for the float value. Floating point value. And probably could have used better terms for each of those, number 4 and 5, but this is where we're at. So we know that the sign bit at this point is 1. We know what the fraction is. 1.97. Oh my. 1.9375. And we calculated that the exponent, didn't really calculate it. We know its binary value in decimal is going to be 10. We did calculate the bias, and we said that that's going to be 7. So using that information, we can then use our normal calculation, and the value for normal is going to be equal to 1 multiplied by the fraction value, which is 1.97. Oh my gosh, 9375 multiplied by 2 raised to the value, the binary value of the exponent, which is 10, less the bias, which is 7. And that's going to give us 31 seconds. And I do have that written down. And that is 15.50000. The reason I did that is that's what you can expect. 6 positions of precision when you do your program. That's what you should get for a float. Anyway, that is the normal calculation. I'm going to do another video on denormalized and walk through that as well. Again, if there are some errors in this, I'm sure there are. I apologize for that. I did take a little more time on putting this PDF together. There might be some errors in here as well, as far as maybe spelling or something like that. But these formulas are correct. What they represent are correct. And hopefully between the video and this PDF, you can get through your program with relative ease. So thanks for watching. Appreciate it.